So now our quest is to introduce this dielectric resonator concept to this already designed antenna. Now, as mentioned, this dielectric resonator is basically a block of dielectric which is devoid of any metal. So we will remove this metallization, and in terms we will reduce this conduction loss to a huge extent. Now this dielectric block which we are considering is basically constructed on the same side of the substrate as the patch. So I have selected that face only. I mean, if I show you these components, you'll see that the front side of the surface is being substrate is being displayed. And to give us an idea about the coordinate, I will select only this patch so that this wireframe, this graphical maze comes and we can have an idea about the dimensions of this patch. Now see this annular square ring at the center that basically has the dimension of 4 cross 4. Sorry, 8 cross 8. 4 to minus 4, again 4 to minus 4, like this. Okay. So let us consider that we will place the dielectric block centrally, I mean on this annular patch, such that it covers this annular patch completely. Okay, that means if you see from the top, that means I mean the view in which we are seeing the structure now, if I place this dielectric, you won't be able to see this annular patch. Let us design it in that way. So for that, we need to remember that this minus 4 to 4, the x varies from minus 4 to 4, the y also varies from minus 4 to 4. We need to remember that. Now again, there is a very large amount of flexibility in design according to the shape of the possible dielectric slot, dielectric block. That means you can design a rectangular dielectric slab, a square dielectric, circular dielectric, cylindrical. I mean, we are designing a 3D shape actually. Any possible shape is there. The choice is depending upon us, what shape we want to incorporate and what particular results that they will give us. So I will show you to design two different types of dielectrics one by one. After that we will simulate. So for that, let us consider that at the beginning we are designing a square dielectric block or a square dielectric resonator. So as I mentioned, the square dielectric resonator will sit at the central position of this patch and it will cover this annular ring completely, annular slot completely. Okay. So we are designing a square dielectric. So we will select modeling. Then we will select this brick, because already mentioned for designing square structures or rectangular structure, we have to select this brick. Brick, select and click on escape. This brick profile will come. Now we need to name it. Okay. Suppose DR dielectric resonator, put an underscore, square. Or let's make it a bit more general. Let's make it rectangle. Let's make it rectangle. See, x for this annular slot, x varies from minus 4 to 4. We will make it a bit larger. Say, we will make it minus 6 to 6 or minus 7 to 7, for example. So x min is minus 7, x max is 7. Okay. Now y min. Here y min is minus 4 to 4. Y varies from minus 4 to 4. That means the total length is 8. Here the total length is 14. Let's make the total length to be, for in the y direction, to be 10. So if the total length in the y direction is 10, we will select minus 5 to 5. So let us select minus 5 to 5. So the length along the x-axis, along the x direction is of 14 units, and the along the y-axis, the width is 10 units. So it is a rectangle. Now the trick comes while selecting Z-min and Z-max. It's very tricky. Visualize the structure. Visualize the structure. Where shall we place this dielectric block? Now imagine, as I am saying, you should imagine, we are placing this dielectric block on top of the metallic patch, which you can see, this Hilbert patch. So what are the things that we are having? First, we are having the substrate. On top of the substrate, we are having the patch. On top of that patch now, we are placing the dielectric resonator. So what was the top level of the substrate? 1.6. What was the top level for the patch? 1.602. On this top level, the DR will sit, the dielectric resonator will sit. So the top level of the patch should be the bottom level of the dielectric resonator. This trick you have to understand. This method you have to note and you have to follow. So what was the top level for the patch? 1.602. So Z-min, the bottom level for the dielectric resonator, Z-min for the dielectric resonator will have the same value, 1.602. Now we are designing a 3D structure. The length of the 3D structure we have defined 14 units. The width of the 3D structure we have defined to be 10 units. Now we need to define the height. Suppose the height is, say, 6 units. For example, I am giving you. Or 7 units. Let's take 7 units. So from this bottom level, it should extend to 7 units. 7 units more. That should be the height. So we have to add the height amount. Here it is 7 to this Z-min. So if I add 1.602 and 7, I will get Z-max as 8.602. I hope you have understood. 1.602 is the minimum bottom level. From that we are getting a height of 7 units. So Z-max, the top region, the top portion, the top level comes to 8.602. Again, we will not do anything with the component. But certainly, this dielectric is not a metal. So we need to change this PEC. Okay. So again, we will put the drop down. Now this is not FR4 because the FR4 dielectric is defined for the substrate only. We will not define the same dielectric for the dielectric resonator also. We have to select some new dielectric, some different dielectric. So what we will do, we will load the dielectric from the material library. So load from material library. Again that list comes. See, you may have different options here, different options, wide range of options. Okay. Now, the most commonly used dielectric for preparing these resonators is alumina or quartz. Okay. So let us select alumina only, which you will find at the very beginning of the list. See, alumina. Alumina loss free, alumina lossy. Again loss free, again lossy. What is the difference between these two different these two lossy varieties? See this percentage. How much lossy it is? This is 99.5% pure. That means 0.5% lossy. This is 96% pure. That means 4% lossy. So let us select the better one. So let us select alumina 99.5% lossy. So we will select this one. Now the moment you select this one, see the epsilon, the permittivity of this material is getting defined. Permittivity along with the other parameters, the other characteristic features, these also get defined like this. See the value 9.9. Now this is an automatic design methodology that okay, we are not using FR4 for the dielectric resonator, we are using something else. So how will we define something else? What else, what other dielectric we can actually use? That dielectric should have the permittivity sufficiently higher than the permittivity of the material which you have used for the substrate. Now for the substrate which we have used the FR4, which if you remember had the epsilon, the permittivity value to be 4.3. Now we are selecting alumina, which is seen here to have a permittivity value of 9.9. Okay, so you can select some others also which may have some other values of epsilon. For example, see, if I take uh, this quartz which I was talking about, okay, if I take this quartz, I think we will get a high value. See, quartz lossy. No, it is actually low. So we can select something else. For example, see, if we select some polycarbonate material, okay, organic polycarbonate material, okay, porcelain, mica if we use, okay, mica is also having 7.9. This can also be used in some situations, okay. In some popular research, foam is used, although I can't see this foam here. Different types are possible, okay. Different types of substrates are dielectric materials are possible. So let us stick with alumina. I'm not finding that particular material in the library now. So let us stick to alumina 9.9. Now you should load. Now when you load, this alumina comes under the material. Okay. So we have defined it properly. Now let's preview. See, this outline comes. That means the structure is properly defined. Now if you place OK, already simulated results were there, so it is asking whether we should delete those simulated results or not. You can choose your option. Let me delete because I will start the simulation from the beginning. Okay, see, it is getting defined. Now if I rotate it, see, it is getting defined. Can you see this dielectric sitting on top of the patch like this? Okay, and it is rectangular one. Now here we may confuse in one thing, the substrate, this substrate and this dielectric block, resonator block, they are of the same color actually. So we can change this color. I mean, we can right click on this dielectric. This under component, this dielectric rectangular is there. The way we name the structure actually, dr underscore rectangle. So we right click on this, and from the pop-up window, we select this material properties. See the second last option, material properties. Let's select it. The window that opens, see, epsilon mu is there. Okay, you can change the value here. I mean, if you want a higher value, you can do that. Okay, I mean, I can make it suppose 15 possible. If I apply, this new value will come. For the time being, I'm not doing that. It can be done. Okay, see, color is there. Select on it, select on this bar. This color bars are there. Now select any particular different color, I mean, which should be different from the substrate, identifiable from the substrate. So let us select this yellow one. Put OK. This yellow is selected. Apply. OK. Now it will not be shown here. Again go to components. Now see, the color is different. So in this way, you can actually identify different components by assigning different colors to them. Okay. I can even make the substrate differently colored if you want. If you don't like this pink color, for example, right click, material properties, By default, this pinkish color will come. Let us say that we are selecting this light sky blue. Apply. Okay. Apply. Okay. Components. Now see. Okay. Whichever you want, you can do, but it should be identifiable, because if you want to create any particular design, then that particular design should be identifiable as separate components in your overall structure. So this is the overall perspective view. Now, if I show you the front view, see, as planned earlier, this dielectric is completely sitting on the patch. I mean, if I show you the patch now, see, this is the patch. See, this is the patch. Not the patch, sorry, the slot. The dielectric is sitting on this slot and it is hiding the slot completely, which is what we planned, which is what we intended to do at the beginning. Okay. So now if I select the components, see, the slot cannot be seen now. Okay. So this is the perspective view. And so our dielectric resonator, rectangular dielectric resonator, is actually prepared.